You are watching the 4.5 lesson video on comparing linear and exponential functions. So just a quick recap. Linear functions. We should know that if we're dealing with linear functions, we are repeatedly adding. We call this the slope. With exponential functions, on the other hand, we aren't adding, we are multiplying. And this is going to be the base, the multiplier. Looking at exercise number 1, they give us two different tables, and we're trying to figure out which is which. So I'm hoping that many of you now are used to finding a pattern. So let's go ahead and do that. So what is my pattern in table number 1? How did I get from 5 to 10, 10 to 20, 20 to 40? And the reason why I can do this so easily is because my x values are all increasing at a steady rate. Well, if you said multiplying by 2, you, my friend, are correct. So we have a multiplier. What does this mean? Well, we have an exponential function. All right, looking at table number 2. We have the same thing happening with our x values, only our y values are not being multiplied. We actually have an adding factor of 3. Every single time the x increases by 1, the y increases by 3. Because of this, we have a slope. So this is a linear function. We can say that it's linear because it has a constant rate of change, or it has a constant slope. Now moving into exercise 2, they want us to find equations. So we're trying to find equations. And since they're both y's, I'm going to just start off both equations with y equals. I love that I have my initial values right here. So in table 1, I'm starting with 5, but in table 2, I'm starting with 8. And again, this is my y-intercept, my starting value. And what am I doing with my starting value in table 1? Well, I'm multiplying by 2 over and over and over again. So we will use a power to show this repeated multiplication. Where in table number 2, we start with 8 and we add 3 over and over and over again, and we show repeated addition with multiplication. Okay, exercise 3. We have 2 points, 0, 12, and 1, 3. I will plot those immediately. So 0, 12, it's my y-intercept. I love when I get that point. And 1, 3. And just be careful of your placement. This is 1, not here. All right, so it says create a linear equation and an exponential equation that passes through each of these 2 points. Well, this is interesting. Well, the first thing I probably should do, and I typically do this all the time, is make a table of values for each of these. So let's say that this over here will be the line, and what? We're given the point 0, 12, and also 1, 3. And let's do the same thing over here for the exponential, because this will perform or behave a little differently, or a lot differently. And we'll say that this is the exponential one over on this side. Okay. How do we come up with the equation of a line? Well, if we come up with the equation of a line, we typically have a starting value, which, hooray, they gave us right here. So y will equal, I start with 12, and I need to find my either number that I'm adding by or subtracting by, and I do this by calculating the, you guessed it, the slope. So how did 12 become 3? Well, it looks like I'm taking away 9 every single time, and I always want to check this. My x increases by 1. This is great news because if it had increased by 2, I'd have to divide the minus 9 by 2 to get my actual slope for the every 1 value. So 12, I will be taking away 9 every single time. With my exponential, remember it starts the same way. We will have a starting value at 12. It's still my y-intercept. However, I need to now figure out how did 12 become 3 in a different way. We are not dealing with subtraction, we are dealing with multiplication. Well, some of you might say 12 divided by 4 is 3, but I can't write it as dividing by. What's another way that I can write out dividing by 4? Well, multiplying by its opposite, 1/2. So, sorry, 1/2. Silly me. 1/4. I said it right, or I said it wrong and I wrote it right. Okay, so 12 is being multiplied by 1/4 over and over and over again. And again, we do not need to worry about dividing or figuring out a different type of ratio because my x values are just increasing by 1. All right, let's graph these. Go ahead right now, pause the video, and change your window so the x's only go from -2 to 2, and the y's go from -5 to 15, just like this chart over here. Okay, my window has changed. Let's now graph all, or actually not all, there's only 2 equations. I'm going to graph my line in f of x and my exponential in f2 of x. Okay, here you have it, my 2 functions graphed on the window that they provided for us. And I typically would do this anyways, even if they didn't tell me to graph, because I really want to make sure that what I'm doing is right. So, do I have the 2 points that I need in both of my tables? The point 0, 12, yes and yes. Also 1, 3, yes and yes. And next what I'm just going to do is sketch my graphs. It didn't tell me to restrict the domain, so I'm going to have to play around with this a little bit. Sometimes it's hard for me to graph my lines. Here we have our linear function. And I will label this y is equal to 12 minus 9x. And let me pick a different color. Let's pick red for the exponential. Notice where my asymptote is. It keeps getting closer and closer and closer to what value? Now, you can see my calculator is doing something funny, and some of you might say, oh, it's just going up again and down again, but really, it's getting closer and closer and closer to 0. If you hover over this, you'll see that my number is written in scientific notation. I could even take my graph over here and pull it to see that, it is not going to ever touch the x-axis. So it's doing something like this. And that should be touching. And last but not least, let's label it. Y is equal to 12 times 1/4 to the x. Now exercise number 4 is telling us to find the average rate of change over 4 different intervals. Well, the first thing that I'm going to do is, you guessed it, make a whole bunch of tables. Okay, so you probably just want to pause the video at this point in time, make 4 different tables of values. I don't think that you really need me for them because they were nice enough to give us the table of values. So I'll do A with you. We were given the x values of 0 and 1, and my y values are 4 and 8. Go ahead and finish B, C, and D's table. Okay, now let's find the average rate of change. Well, that's figuring out how did our y's change. Looks like we added 4 here and added 1 there, so my average rate of change for this is 4. What happened here? Well, I added 8 while I added 1, so 8 over 1 is just 8. Same deal for C. We added, 16 here and 1 there, and 16 divided by 1 is 16. What is going on with my rates of change? Are they the same? No, D, I got 32. My average rates of change are growing exponentially. So what is happening as x gets larger? My average rate of change is also getting larger in part E. And an even better way to write this is to say that the average rate of change is doubling, which should not come as a shock to any of us because, oh my goodness, look at this amazing connection. I can't even believe it. There's my multiplier, and the average rate of change is also doubling. We're not looking at a linear function. This is exponential. Okay, exercise 5. We are considering the linear and exponential functions given right here. You know the drill. Go ahead, fill out the table of values. Pause the video, I'll do the same and fill them in so you can compare. Okay, check your tables of values and see if yours match up with mine. All right, moving on. For parts B and C, they ask us to label each function and graph them over a specified domain. So that means I am only going to graph from here to here on this graph and from here to there, both functions on both graphs. Go ahead, pause the video, and while you're graphing, I'll graph as well. Then I'll meet you back. Okay, so here we have our beautiful graphs that are labeled. I even color-coded them for you. Now, part D says, although the line appears to rise more quickly than the exponential at first, the exponential eventually catches up and surpasses the linear function. So why is this going to happen? Well, I think you already know this, because if we multiply by something over and over and over again, as opposed to adding something over and over and over again, we're eventually going to see that the multiplication will always surpass addition. So take a minute to write down the response for part D, and then we are done.